Hello, in today's video we are going to talk about these small little current transformers. So these are small devices that can detect the presence of, let's say, AC current, or it could be something else like square wave or ramp or something like that. But the essential idea is that you pass a wire through this hole, and whenever the wire changes its electromagnetic field, it will be detected by a coil inside, and the coil is here, so it is a tear down of this thing. So whenever that happens, whenever you, let's say, turn on a bulb or something like that, it will detect the change and it will generate some voltage. So as you can see, these are very small. The diameter is the not the diameter, but the size of this is 17.9 mm, and in this direction it is 10.2 mm, and the pin distance is 12.8. Maybe it is plug-in 12.8, and the hole diameter is something that probably I can't measure, or maybe I can. So the hole diameter is 5.2 mm, so you can't actually insert a wire thicker than that. Maybe you can't insert a 6 mm wire here. So that's the thing. And now let's see how these things work. So what I have here is a wire, green color wire, passing through this thing, and the green color wire has a bulb connected. So one side it is connected to the mains AC, 250 volts, 50 hertz, and the other side is connected to the bulb, right? And I have two bulbs. One is, of course, both are 200 watts. And now let's connect these to the oscilloscope first. Polarity doesn't matter because it will generate AC current. And now if I turn on the bulb 1, you can see that we have something, right? So this is quite nice, and we are optimistic that we found something. So if I change the horizontal time base in my scope to, let's say, something like 5 millisecond or maybe 10 millisecond, you can see that it is generating something. If I turn on bulb 2 as well, you can see that we have higher amplitude because it is generating more voltage. If I turn off bulb 1, you can see that the amplitude reduced. Turn on bulb 2, amplitude increased. But as you can see that it is not a perfect sine wave. So what's going on? So these things generate a lot of noise. And to reduce that noise, what you can do is you can just connect one 1K resistor in parallel to the current transformers. So let me just add one 1K resistor. And if I connect the 1K resistor in parallel to this, like that. And now if I connect my scope again, polarity doesn't matter here. Now if I turn on bulb 1, you can see that it is generating nothing because the scope is set to 50 volts and it doesn't actually generate that high voltage. So if I set the scope to auto mode, so as you can see that it generates around 568 millivolt minimum, and the maximum is 592 millivolts, and the frequency is 50.0402 or something like that hertz. So it is a little bit fluctuating because the mains frequency also fluctuates a little bit. The peak to peak voltage is 1.6 volt. You just add these up, right? So the peak to peak voltage calculates the voltage from this peak to this peak. So now what happens if I turn on bulb 2? If I turn this on, you can see that the scope can show that at 200 millivolt, but if I change it to 500 millivolt, now it shows something, right? And it is the same thing, but the peak to peak voltage has increased to 2.2 volts, and now we have mostly double the voltage. So the minimum voltage is 1.080 volt and the max is 1.1 volt. What happens if I turn bulb 1 off? You can see that the amplitude decreases what happens if I turn on bulb 2? It just disappears. If I turn both bulb at the same time, you can see that it works perfectly well. And if I change the time base, so we can see what's going on. And if I turn both the bulbs off, it is gone. Turn both on. So as you can see, there are some also spikes going on when I turn on and off the bulbs. Here it is not absolutely perfect. So if I toggle that again, you can see that there are some spikes, and we can actually zoom in there. And you can see that there is a little spike. And now we are going to test the inductance and all of that stuff with an LCR meter. So let's get this high voltage stuff out of the way, and also the oscilloscope out of the way. Turn this thing off. And now let's take our LCR meter, and we are going to measure the inductance. So here's my LCR meter. Let's power this thing on. This is quite big LCR meter actually, and quite nice that also it can measure up to like kilo Henry, not just Henry but also kilo Henry. If I connect one of these, so let me first connect this black one, and just to introduce you, there are multiple ones, as you can see, except this one. This is not a current transformer. Instead, this is a common mode choke. I have kept this for a good reason that I'm going to show you a little bit later. So let me introduce these current transformers to you. First of all, we have these black ones. These four black ones that have ZMCT102 written, these are actually rated for 20 amps, and these will generate about 5 milliamp. These blue ones are actually rated for 5 amps, and these will also generate 5 milliamps. And this black one, it doesn't have anything written. So if you compare this with the other black ones that I have, you can see that it doesn't have anything written. So this one is just same as the blue one, except the color is different, of course. So this one is also rated for 5 amp max, and it will generate 5 milliamp of current. So let's start the probing. I'll just start with this black one first. I'll change my function to measure inductance, and we are going to measure it in the series mode instead of the parallel mode. I'm going to explain what that is a little bit later. Let's turn on the backlight. We can see that the inductance of this thing is 59.08 Henry. Right, you have heard it right. It is surprising that it is in Henry, but if you see the tear down that I have done, again, this is very hard to do because this whole thing is coated in epoxy, and then you also have a plastic cover, and the whole thing again is just epoxy potted, right? So what I had to do to get this out is I applied a very high temperature, maybe few hundreds of degrees, and the temperature melted the plastic and also the epoxy as well. And what we have here is this ugly looking thing because it is not absolutely clear. Of course, there's plastic bit. Let me actually focus that so you can see. So here you can see that we have a copper winding on a core, most likely, and the copper is very thin, and there's a lot of copper, there's a lot of winding here. It will take me like few days to just do that by hand, and there will be many accidents where I will just rip off the copper because these are very thin. So these are, of course, I believe machine made, because these are literally impossible if you want to do this by your hand. So that's what inside of these things. Now let's focus again. Now you can see that it does indeed have 59.2 Henry because this is very dense and thick, and this is at 1 kilohertz. And if I change the frequency to 10 kilohertz, it drops to 951 millihenry. If I change the frequency to 100 kilohertz, it drops to 9.5 millihenry. So we are not talking about henries here, but we are talking about millihenry, which is perfect, right? And if we check at 100 hertz, you can see that it is 73.8 Henry, which is a lot. At 120 hertz, we have 69.86 Henry. At 1 kilohertz, as we saw, we have 59.05. So these things are not child's play actually. And you might doubt that my LCR meter is bad, right? That's why I actually took this common mode choke. These are 10 millihenry known values. Unlike these ones doesn't have any known Henry values or something like that. But these ones do have, and these are 10 millihenry chokes. And this is a common mode choke, meaning you have a core inside, a toroid core, just like this one. And this toroid core doesn't have full winding like that, but instead you have half winding here and half winding on this part, and you have a isolation in the middle. So what happens is that when you just connect a load here, it will eliminate the common mode noise. So that's the main purpose of this. So this is definitely not a current transformer. Let's measure this thing. If I connect these pins, because you have a winding here in this direction and one winding here to the upper part. Now you can see that it is 12.27 millihenry. It is rated for 10 millihenry, but it is close enough. So my LCR meter is working great. Now we know the value that it is 12.27 or 12.28. We can also connect to the other side, and we should see the same value because the main purpose is to have same winding. So this is exactly the same value, 12.28. So my LCR meter is working great. And we can of course change the frequency to 10 kilohertz, for example, and we get 11.5 millihenry. At 100 kilohertz, we get around 18 millihenry. So it has increased. At 100 hertz, it is 12.435 millihenry. And at 120 hertz, it is 12.468 or 12.48. So my meter is working perfectly well. But these ones are absolute beast, right? I actually didn't expect them to have values in henries, not in henries, but hundreds of henries, as we are going to see in the other ones. So if I connect this one again, and this is different from the black one, of course, but let's start with 100 hertz. At 100 hertz, you can see that it is rated at 67. So inductance is 67 Henry, not millihenry, not microhenry again. And if we change the frequency, but before that, let's also see some other stuff. We have a Q, we have a value called Q, and the Q is 7.25. It is the quality factor. So it determines the quality of the inductor as well. And the higher that is, the better it is. And the inverse of Q is the dissipation factor, or in here it is called D. So the D is 0.138. So the lower the D value is, the better it is. But this is not a very low value, so dissipation factor is not that great as well. So the quality is not that great because of the ESR we have. So let's see what ESR we have. The ESR is 5.8 kilo ohms. So at 100 hertz, it is 5.8 kilo ohms resistance, right? So that is a lot because of course you can see that it has a lot of winding. And if we change the frequency to 120 hertz, you can see that ESR probably stays the same, but the inductance differs a little bit. At 1 kilohertz, the ESR is now 0.2 mega ohms, and the inductance has increased and jumped up to 105.7. And the ESR is terrible, right? And that's why the Q factor, the dissipation factor has increased. The Q factor has also decreased because it is a low quality inductor at 1 kilohertz. And we also have another thing called the theta, or the phase angle, and the phase angle is 67.7 degrees, meaning that it is not a pure inductor. It also has some capacitance, probably few picofarads or so, maybe few hundred picofarads actually. So that's why it is not really ideal. It is like, if you want to use these things as inductors, just be careful. These are not really good for inductor purpose. These are not made for that. So let's switch to our ESR, and it is now 0.2 mega ohms, which is very high. And if we change our frequency to 10 kilohertz, it is now the ESR has decreased to 3.67 kilo ohms, and the inductance has decreased to 1057 millihenry. So we had 100 Henry. From 100 Henry, it just dropped to 1057 millihenry. So that's quite interesting. Maybe it just resonates at 1 kilohertz or something like that. And again, if I change the frequency to 100 kilohertz, the ESR is now 0.2 kilo ohms. So it is like 200 ohms or something like that, 250 ohms. And the inductance value is 10.789 millihenry, which is kind of close to this one, 10 millihenry choke. You are going to probably use that at AC frequency 50 hertz or something like that. In that case, of course, it just works the way it should work, but if you use that as inductor, it is not going to work. And now let's get this out of the way, and now let's measure these ones. These are based. We are starting from 100 hertz. The inductance is 243 Henry. Again, not microhenry, not millihenry. And the ESR is 35.3 again. The phase angle is 76, which was probably better than the blue one. And the dissipation factor is 0.23. The quality factor is 4.3. And if we change the frequency to 120, we can see that the quality factor has increased a little bit, which is great. Let's actually measure the ESR. It is currently 38.4 kilo ohms. If we change the frequency to 100 hertz, the ESR is 35.6. For 120, it was 38.6. The Q factor is, for 100 hertz, it is 4.31. For 120 hertz, it is 4.6. And the D factor is 0.215 for 120 hertz. And for 100 hertz, it is 0.234 or 0.233, something like that. So that's good. Now let's change the frequency and see how it works in different frequencies. Now if I change the frequency to something like, let's say 120 hertz, it reduces a little bit, and at 1 kilohertz it drops a lot. At 10 kilohertz it is now in millihenry, right? And at 100 kilohertz it is like the common mode choke or the other ones that we saw. Now also let's measure this thing in the parallel mode. So in the parallel mode, it is just like connecting a resistor in the parallel. So we assume that we have a resistance in the coil inside, connected to parallel, and that's a different measurement mode. Currently we are measuring in series. That means we are assuming that there is a series resistance to this coil, right? If I switch to the parallel, you can see that it kind of fluctuates a little bit at 10 kilohertz. But if we switch to 100 hertz, it is 270, close to 270 Henry. At series, it is like 253 Henry. At parallel, close to 268.5, something like that. And if we change the frequency at 120 hertz, we are down to 255 Henry, and for the series check, we have 242 Henry. So that is quite interesting, and the ESR should also change. The ESR is 41 kilo ohms at 120 hertz. And in parallel mode, we also have a resistor of 0.8 mega ohm, right? Which is great. Now let's switch to capacitance, shall we? So the capacitance says that in the parallel mode, we have 6.916 nanofarad capacitor. But in the series, we have 7.26 nanofarad capacitor at 120 hertz. If I change the frequency, it increases a lot. Now it's 170 picofarad capacitor. If I change to 10 kilohertz, now it is 246 picofarad capacitor. At 100, it is 240 picofarad. So it just hovers around 200 to 250. And if we change to series, we have 240, and for parallel, we have close to 240, I will say. And if we change the frequency to 100 hertz again, it is 9 maybe 10 nanofarad. And if we change the mode to parallel, it is also close to that as well. So yeah, these current transformers are very interesting stuff. I also hope you found this video interesting. If so, please give this video a thumbs up. That will help the channel. And don't forget to subscribe if you like the video. If you don't like the video, please comment below for any corrections or such. And I'll see you in the next one. Thank you. Cheers.